This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so let's get started on Friday afternoon. So in the last lecture, we discussed review the second law. And the second law is saying that a different form of energy, they are of different quantity or different capacity to be converted to useful work. And there we learned, we didn't learn, but we reviewed the concept of entropy. And entropy, as we said, we're using a capital letter S. Entropy by definition is an extensive property, and it has a dimension of joule per Kelvin, which is different from the energy, which is only have joules. And entropy, how do we calculate entropy? We discussed the Gibbs equation. So Gibbs equation can be written as, in order to determine the entropy change from one state to the other, we can write as CV log T2 over T1 plus R log V2 over V1. So that's one form. Or if we write in terms of the pressure, we have Cp here, then minus R log P2 over P1. All right. So the function or the purpose of deriving the Gibbs equation is so we can calculate the change in the of entropy from one state to the other. And the when we're deriving the Gibbs equation, if you recall, we started from a system which is a closed system and going through a reversible process. And people later realized that when they apply this equation, actually this equation is more universal. It can apply to irreversible process as well as open system. So that's just turned out to be the case. So this is a Gibbs equation is a universal way to calculate the entropy change. All right. So I should say it's applicable for irreversible process and open systems. All right. The reason that we discuss the Gibbs equation is we want to derive an equation which is more useful, or we used extensively in the later psychoanalysis, which is isentropic relation. Isentropic means this process is where the entropy, where the entropy does not change. So it's called isentropic. So the process has no change in terms of the entropy. So to derive this equation, which is pretty straightforward, given we already have the Gibbs equation, right? The Gibbs equation, if we let the left-hand side to be 0, then we can just derive the temperature-pressure variation along an isentropic process. So that's the purpose of there. So we just let the Gibbs equation to be 0. Equals to 0, then we can find the relation of temperature, volume, or temperature pressure there. All right, so let's quickly going through that. So we have the CV. So if we do the first one, the CV log T2 T1 plus, let's start with the second one, which is P2 P1 equals to 0. Right? Then I just rearrange terms. So log T2 T1 equals to R divided by CP. CP over there. Log P2 over P1. Then we can further write it. So the R is gas constants for the specific gas we're dealing with here. And we mentioned that for ideal gases, the R can be written as Cp minus Cv, right? For ideal gases, then the Cp and log P2 over P1. So if we divide every term here by Cp, not by Cp, by Cv, right? Then we have bring the definition of the Cp over Cv equals to gamma. Then we have the gamma minus 1 and the gamma. Right? Divide everything by Cv. Then we have the log P2 over P1. Then we can find the relation in terms of the temperature and the pressure can be right in this form. All right, so that's the first equation. We can certainly write in different combination in terms of temperature, volume, or pressure volume, right? So if you want to write in terms of volume, there will be V1, V2, gamma minus 1, and the pressure P2, P1 will be V1, V2, gamma. So these three altogether being called isentropic equation or isentropic relation, isentropic law, this kind of terms. And what the function of this? First, this applicable to the ideal gases, not really applicable to condensed matter, liquid or solid. Does not really applicable. Applicable for ideal gases, and it describes that if you have ideal gas to going from state 1 to state 2 with an isentropic process, then you will end up with temperature, pressure, and volume in that relation, right? It describes from start to the end. So that's different from the ideal gas law we typically refer to. Let me just so this is isentropic relation for ideal gas from state 1 to state 2 via isentropic process. It describes the outcome of a process. And this is different from ideal gas. What ideal gas stands for? Ideal gas law stands for. Ideal gas law does not describe a process. Ideal gas law just describes for a given state how the temperature, pressure, and the volume should be related for ideal gas, right? It doesn't describe process. This one describes a process, and what the temperature and the pressure should end up with. Ideal gas law just describes a given state. There is no process involved. All right. So this relation and the ideal gas law will be the primary tool later on when we're dealing with the gas turbine cycles. All right, so that's the isentropy relation, and there is when we're discussing the cycle cycle chapters, there is a few components or few devices that we consider the process happening in those devices isentropic. So let's have a look at them. So later on, when we're talking about the cycles, that's more straightforward. So isentropic device in psychoanalysis. So let's consider if the problem saying the process is ideal process, and that ideal process is isentropic process. Then you can apply the ideal gas law we just mentioned. The first one is a compressor. Compressor is something to raise the pressure of a gas. And the purpose of it, raise the pressure of gases. And during that process, the external work is being added to the system where the containing the gas, and converted into the enthalpy of the gas. So external work is converted to enthalpy in that process. So one type of a compressor that you can have a look is, it's called axial compressor. So this is a type of compressor is commonly used in gas turbines, whether the gas turbine is used for the power generation or for aircraft engines. So basically, you have the ambient air coming and then going through a layer of blades. So the blades is basically one layer of blades that's rotating, called a rotator, and another layer of blades which is does not move, that's called stator. So rotator, stator, rotator, stator, there are different layers corresponding to different stage of compression. But the purpose is to increasing the pressure of the gas, and by doing that, the external work being converted to enthalpy of the gas, right? And the compressor certainly can come in with different design. This is just one type. You can just using the piston compressor, which is similar to a car engine, but the purpose of it is not to output the shaft work, but just to compress the gas, to produce a high pressure gas as the output, right? So that's the compressor. Okay, maybe there is a few more examples. Maybe I discuss all of them again, then I show the slides to avoid switch back and forth. All right, so the other one is called a turbine, where we consider the process, if it's ideal, the process going through it is also isentropic. Turbine, you can consider that's the opposite of compressor. Turbine is a process where the pressure will be dropped for the gas, and in that process, the enthalpy of the gas being converted to useful work. And another one, so these two, you can consider they are a pair. Actually, in practice, if you're looking at a gas turbine, often the turbine and not often, always the turbine and the compressor, they are on the same shaft. So it's a coaxial design. And another pair you can consider is called a nozzle, which is another component when we're talking about the gas turbine cycle we are involved. Nozzle is a device which you have enthalpy at the inlet, and then you have the kinetic energy at the end. So you can consider it's similar to turbine. It will drop the pressure, but the purpose is to convert the enthalpy to the kinetic energy. So to produce the high velocity gas at the exit of the nozzle, so that it can produce a thrust to propel the aircraft, right? And the opposite to it, that's called the diffuser. And the diffuser is something which is to raise the pressure. And there you have the kinetic energy coming in, high velocity gas coming in, and converted to the enthalpy. All right, so an example of the turbine is showing here. This is it's actually a gas turbine. No, it's a steam turbine, used in the steam power plant. And what's showing here is only the rotor, and between each rotor there should be stator, which is not showing here. You can see their size can be enormous in the power plant. Nozzle. This is a military aircraft. So here you can see that's the nozzle where the combustion or the combustion part, which is happening somewhere here, and then going through the turbine, and at the end of the turbine, then you have the leftover enthalpy, which is going through the nozzle to produce the thrust. All right, this is a twin engine aircraft, and at home this is like home use nozzle. So basically, you have the higher you have heaters around here, and then you're using a shrinking diameter of design to increase the velocity. Right, diffuser. This is an example of diffuser. Basically, if you consider the Bernoulli's principle, when you increase in diameter, the velocity will drop and the pressure will goes up. So that's basically the diffuser here. So turbine, compressor and turbine, we will use in the gas turbine cycle and the steam turbine cycle, and the nozzle and the diffuser will be also using the gas turbine, which particularly is a cycle called turbojet cycle. We will have the diffuser and the particularly nozzle there. All right, so that's several devices where we consider the process going through them as isentropic, so that we can apply the equation we just learned to calculate the temperature, pressure, and the volume change going through these devices. Another thing we want to discuss, which is at the end of the introduction chapter, is called Carnot cycle. So we said the second law saying that not all heat can be converted to work. Right? In a heat engine, not all heat can be converted to work. But what's the limit? How much heat can theoretically be converted to work? That's this Carnot theory or Carnot cycle is about. So Carnot cycle, let's just write a few words. So theoretical limit for heat to work in a heat engine. Carnot cycle is basically 4 steps. So the first step is, let's say if it's from 1 to 2, it's isothermal heat addition. Then the second step is isentropic expansion, and then is isothermal heat rejection. And the last step is isentropic compression. All right, so we must use some kind of diagram to show this. And the diagram we choose here is called the TS diagram. Temperature versus the mass-specific entropy. So this one is joule per Kelvin per kilogram, mass-specific entropy. And the reason that we can use these two parameters to describe the process is because again, state postulate. Yep. That's the things we mentioned in the first chapter, first lecture. If you have we're dealing with a simple compressible system, where if you apply the state postulate, it says the state of or the whole system can be described by two independent and intensive properties. Right? We consider temperature and entropy certainly independent, and this one is intensive, and if you normalize by mass, the entropy is also an intensive property. So two independent intensive properties can describe the whole process. So that's the starting point here. So we choose TS diagram. It can be drawn by different combination of parameters, but we use TS here. So the first step saying that isothermal heat addition. So if you have isothermal process, if I from here, isothermal process, how should I draw the line to get the state 2? Yeah, a horizontal line to get the state 2. Yep. So in this process, it's called the heat addition. So you have the heat transferred from the high temperature reservoir to your system, right? And then it's a isentropic expansion. So if I want to go to state 3, how should I go? Going down for sure, and going down along a vertical line, right? So it's isentropic. So isentropic means entropy does not change in this process, so it must be a vertical line. And then this process is doing some workout, because it's expansion. And then the 3 to 4 is also isothermal, so I draw another vertical line here. And this process is heat rejection. So it dumps some heat, unused heat, to the low temperature reservoir there. And the last step is isentropic compression. So another vertical line to return to state 1. And in this process, there is certain input work being done to the system. All right. So essentially, for a Carnot cycle, on a TS diagram, is a box. It's a rectangular box in the on the TS diagram for the theoretical Carnot cycle. Right. All the cycle later on we'll see for the more practical sense they are not a box. So here. They said the Carnot cycle is the theoretical limit for a heat engine. So let's determine what is the theoretical limit here. Say the Carnot cycle efficiency. So this is the thermal efficiency, which is the definition of the efficiency is how much useful in this case, how much useful work you can output from a cycle versus how much energy you need to put into the cycle in order for that process, for that work to be done. Right? So the numerator would be what's the useful output of the cycle. So here we can write W out minus W in. That should be the net work. That should be the useful output of the cycle here. And the required input to drive this process to happen, that would be the heat transfer from the hot reservoir. All right, so we can rearrange this QH minus QL divided by the QH. And the reason I can write this, I can have this net work equals to the net heat transfer to the system, is because if I apply the first law to a cycle, I should be able to get this. So if I do that here, so you apply the Q minus work minus delta U. Let's say it's a closed system, just for the purpose, but it doesn't really matter. So if you do this is the first law, right? First law must be obeyed, like for all the process happening here. If you apply this to a cycle, all right, and you integral, and you integral there, right? What's the left-hand side, right-hand side equals to? Yep, it must be 0. So that's saying the total work or the total heat or net heat must equals to the total work output into the system. Oh, sorry. Right, so that's why we can just rearrange the things here. And if we continue from there, we can write 1 minus QL divided by the QH. So this one sets the theoretical limit for heat engine. And this one is not so straightforward. We can further simplify just based on this theoretical cycle. So if we further write the QL, oh, let's say the QH first, all right? The QH, because this is a certainly it's an ideal cycle, which is a reversible. The Q, the heat transfer, can be written in terms of the T delta S. Right? We said for a reversible process, the heat transfer equals to the TDS. Right? And the TDS, in this case, the T is a constant, the temperature is constant, equals to TH, let's say it's a TH. And then the change in entropy would be S2 minus S1. Right? So similarly, if we do the QL, the QL is this case, if we write in terms of the Q from one step to the one step to the other, so from state 3 to 4. This step is a heat rejection process, so the Q is supposed to be negative, but we only dealing with positive here, so just dealing with the absolute value here. So then we can write TL equals to S3 minus S4. Right? We know it's isentropic process, so S2 equals to S3 and S1 equals to S4. Right? So if we bring this relation back to here, we can find the then we can find for the Carnot cycle efficiency can be written as 1 minus TL divided by the TH. So that's more straightforward way to understanding things. So this one is saying that for the Carnot cycle, the theoretical efficiency for heat engine is limited by the temperature ratio of the hot reservoir versus the cold reservoir. If you can make the hotter, this term will become smaller, the efficiency will goes up. If you can make the colder, then the efficiency, this term will also become smaller, then the efficiency will goes up. So this principle will later on when we're discussing the different cycles in terms of how to improve their efficiency. But here is a more straightforward equation in terms of understanding the Carnot cycle. And if you looking at a typical example, for example, if you have a car engine, right? Car engine exhaust temperature is typically TL is around 1,000, let's say somewhere around 1,000 Kelvin. It's 700 degrees C also. If you consider the TL, in that case, is 1,000 K, and the TH is where the combustion happening inside the engine. So the flame temperature considered as a T high is around 2,000 Kelvin. So we can roughly estimate if you have a car engine, what's the theoretical limit here. So that can be, you can find that the Carnot efficiency is around 50%. So theoretically, a car engine can reach 50%. But the engine or the car that we use today is far below this point. So the typical petrol engine is about 20 to 30% thermal efficiency. The amount of fuel energy you put in versus the mechanical work you can get out of the car. It's only 20 to 30%. So that's it's still far away from the theoretical limit. Diesel engine is more efficient. Diesel engine is typically 30%, on average about 30% more efficient than the petrol engine. 30%, I mean the relative term. So absolute term, diesel engine is about 30 to 40% in terms of thermal efficiency. So relative to petrol engine is about 30% more efficient. But for both engines, they are still pretty far away from the theoretical limit. So if you consider the volume of the vehicle that is out there running every day, if you can improve 5% or even 2 or 3%, there is a big saving in terms of the energy and in terms of the emissions, right? So this one is compared to typical petrol engine. So that's a large improvement can be done. All right. So that's the Carnot efficiency, and if we want to understand this TS diagram further, we can have further insight by looking at the diagram here, and so if I looking at this TS diagram, as we said, the heat addition from the high temperature reservoir can be written in terms of TH times delta TS, right? So if you're looking at this term, this product corresponding to the area on this TS diagram, so this is TH times S2 minus S1. It should corresponding to the area which is underneath TH and from the T1 to T2. So if I can draw this, I should have a corresponding to this hashed area, right? The TH times the difference in terms of the entropy. So that corresponding to the QH. So I can write the QH equals to the area. If I call this as A and this B, area from A, 1, 2, and B. Right, that's corresponding to the QH. And the QL, similarly, corresponding to the TL times the entropy difference here. So that can be written as the area of A, 4, 3, and B. All right? And then what the work or the net work stands for in this case on the TS diagram in terms of the area. The difference between these two? Yes. So if I can have the minus W in, that should equals to the net work, right? That should equals to the QH minus QL, then should equals to the area, area of these two. So that's corresponding to the area enclosed by this box. Area of 1, 2, 3, and 4. All right, so if I just to make this cross area would be the QL, and the box area or the rectangular area would equals to the network, not the input or output, but the difference between these two works. So this one saying that. Because TS diagram we are using throughout our cycle analysis, right? So although there are different ways to plot the cycles, in this study we just choosing using the TS diagram. We're using throughout the 3 cycles we're going to study. So if you're looking at TS diagram, you can have a quickly have an idea in terms of whether the cycle is efficient or not, because the area enclosed, in general case, the area enclosed by the 4 steps corresponding to the network, and the area which is below the high temperature line, the entire area below the high temperature line will corresponding to the total heat input for the cycle. So if this area, this box area versus the total area have a larger fraction, which means the cycle is. So the ratio of this area, 1, 2, 3, 4, to the total area will corresponding to this term, right? So this box area corresponding to a network, and the total area A, 1, 2, B corresponding to total heat input into the cycle. So if this area corresponding to a larger fraction, which means the cycle is more efficient, has higher thermal efficiency. So if in a certain, if the discussion changes the condition, which somehow change the area of this network based on the change versus the total, you can directly tell how efficient, how the efficiency of the cycle we are going to change. All right, so this is just the start. Later on, when we discuss the specific cases, we will emphasize them again. All right, so I can just put it here. The Carnot efficiency equals to the area of 1, 2, 3, 4 versus area of A, 1, 2, and B. All right. So just as I said, we can using different pair of independent intensive properties to draw a cycle. So we choose to use a TS diagram. We can also using other diagrams. Just quickly to show you the it's not the TS diagram. Other combination also possible. We can use a PV diagram. The pressure versus the specific volume. So it's a meter per kilogram. The specific volume, mass specific volume, right? So in this case, we can also draw the cycle, draw the Carnot cycle, and draw any cycle if we want. So in this case, let's say we're starting from state 1. It's an isothermal heat addition. So in this process, we'll have a curve. It's not a straight line anymore because it's a pressure and the volume, none of them are constant in this case. Going to state 2. And in this case, actually, you should follow the PV equals to RT condition. At the start, at the end, the temperature are the same. It's isothermal process, right? The temperature is the same, so the PV should equals to a constant. So you should draw a function of a PV equals to a constant here. And then you have isentropic expansion. Then the volume further increase, but follow another, you can call another slope, another curve going to the state 3. And in this case, you would have the PV gamma equals to a constant, because this process is a isentropic. Isentropic, if you do the pressure and volume, they should follow this equation. And then the other two, just reverse it. State 4, which is also constant pressure, constant temperature, and then 4 to 1 is isentropic again. So which is also PV gamma equals to a constant. So 3 to 4 of those, and 2 to 3 PV gamma constant, and 4 to 1 is also the case. So this is just to show you that not just the TS diagram, we can draw different ways, but apparently TS diagram is more straightforward in terms of Carnot cycle, and also in terms of the later cycle we are going to discuss. All right. Before we finish here, I should say the Carnot cycle is sets the theoretical limit for heat engine, but the Carnot cycle is not really practical. If you want to, in reality, if you want to build an engine, try to approaching the Carnot cycle, I encourage you not to do that. And I have a few discussion that can help you to understand this. So if you consider, maybe just write the statement first. It's not a practical process. So for example, for the process we discussed here, it involves two isothermal process. Right? The first one is isothermal heat addition, and the third one is isothermal heat rejection. Right? How do you achieve an isothermal heat addition process? The heat, if you want to gain heat from a high temperature reservoir, you rely on heat transfer, right? And the driving force of a heat transfer to happen is a temperature difference. You need the temperature to be different in order for the heat to be transferred from the hot to cold, right? But the process saying you need to have an isothermal heat addition process. So heat needs to be added in an isothermal way to the system, which is, if you want to approach it, you have to have the process happen very slowly. So at every step, you add a tiny bit of heat from the outside, and then quickly convert that tiny bit of heat to a tiny bit of work, then reject a tiny bit of unused heat to the cold temperature reservoir, right? So the process must happen extremely slow in order to approaching the Carnot cycle. So that's saying that if you want to produce 1 kilojoule of work, yes, you can do that, and you can do that very efficiently. But the process is very slow. So the kilojoule, 1 kilojoule, you can produce very efficiently, but you need a long time in order to realize that process. Right? So in other words, another property, another factor will be very, very small, which is power. Kilojoule per second, right? The power will be very, very small from that process. And if you want to achieve a comparable power with another device, which is not running on the Carnot cycle, you have to build a huge system in order to produce similar amount of power. So in other words, the engine must be very large, which means you have to spend a lot of investment. I mean, all the volume, all the kilogram for engine, that's equal to the investment, equal to the dollar you have to put in there to build it, right? So the process is can be very efficient, but have a very low power density. What we call power density is the power per liter of the engine or power per kilogram of the engine. Very low power density, which will make it almost useless, even though the process is very efficient. All right? So the different concept, efficient is a good thing, but you also need to consider other parameters or other specifications for practical use. For example, if you want to have an engine to drive a car, right? If you build a Carnot engine, it's very efficient compared to any other heat engines, but itself weighs 10 tons, right? It cannot even move itself. How can to drive people and drive like driving goods, right? So that's something we want you to understand. Thermal efficiency is one thing. We want to improve the efficiency, but at the same time, we also don't want to forget other practical requirements. So let me write a few statements. So isothermal heat addition means extremely slow process. Which means low power or large engine for the same power. So leading to the extremely small power density. Which is watts per kilogram of the engine. All right, the power density can be defined in different ways, either per kilograms of the engine or per liter of the engine. So, but in any sense, you need a large system in order to have a process approaching the Carnot cycle. All right, so that's pretty much it for the first chapter. We got 5 minutes. Let's get started quickly on this chapter 2, which is gas turbine engine. So gas turbine is one type of combustion engine. From the energy conversion standpoint, a combustion engine, as we said, is converting the chemical energy that's stored in the fuel to the thermal energy, raising temperature pressure of the working fluid, then converted to the mechanical energy. Right? So this process is, I should say, is inherently inefficient. And the reason for that is, if you consider the quality or the ranking of the different energy form, chemical is a high quality, and the mechanical is also a high quality in terms of the potential or capability to be converted to work. Thermal or heat is not. It's a low quality form of engine. You go from high to low, the process can be very efficient. This process can close to the 100%. But from low to high, that's inherently difficult. So that's limited by the second law. That's where the Carnot theory is coming into the play. That limits you from getting all the heat to be converted to work. So this process is inherently inefficient, even though today it's still extensively used. There is a new process being developed. So that's called, you can bypass this process from the chemical to electrical, then to mechanical. Any idea in terms of what device can achieve this process, energy conversion process? Fuel cell? Yep, that's good. I'm glad to hear fuel cell first. There's another more common one. I assume. Yep. Battery. Fuel cell achieve this process more directly. It converts the fuel cell, for example, fuel cell car carry fuels, and convert that fuel to electricity through the electrochemical process, and then when the electricity can drive the electrical motor. And the battery actually is, you need external electricity to be converted to chemical first. Battery essentially like it has chemical inside. So external electricity being converted to chemical energy stored in battery, and when battery is working, it converts that chemical energy to electricity, and then the electricity to drive the drive the car or drive other loads. So these are the new process which can, they are not limited by the Carnot theory or Carnot limit. That's the important thing you want to know. But they are relatively new, and they are not, today in terms of the application, it's certainly still dominated by the combustion engines. So if you consider the road vehicle, currently the fuel cell and the battery cars account for about 1%, and the rest, 99%, are still running on the combustion engines. But I should say they are coming very quickly. So people estimate it will account for about 10% in next 20 years or so. Yeah, all right. So that's all for today. Let's continue Tuesday.